Good morning, geometry. Welcome back. Today we're going to look at chapter 15, section 4. We're going to look at segment relationships in circles. And I think before we get into that, again, you guys haven't seen me in a while, so I thought I'd go down memory lane. Again, I found a photo from 1974. I would have been 15 years old. This was, based upon the picture here, this was in the backyard of my aunt and uncle. That would have been my mom's sister. And we probably had a picnic that day, 4th of July. There, look at that handsome little guy. 1974, 15 years old. Cute little guy. All right, then go a few years later. This is your teacher as a senior in high school in 1978. Probably a graduation party. Me decked out in my, I had a three-piece suit. Mom wanted me to wear a suit. That's all right. That's me, 1978. I was a senior. Woo, man, that's a long time ago. And again, here is Mr. Rowe now. Have a great day, guys. Mr. Rowe is a senior, and Mr. Rowe is a senior citizen. Oh, I thought I'd give you guys a little humor. I pretty much haven't changed. Still a little devil. All right, let's look at chapter 15, section 4, segment relationships and circles. Another relatively easy section, so we'll just go and focus on the definitions and the theorems, and just a good portion of this is just algebra. Okay, ready? The first thing we're going to look at is, in part of the Explore, is looking at the segment length relationships in a circle. So again, I have a circle here, and we have two chords. So again, we have the chord DC and the chord EF, and they seem to intersect at a point G. And we can, if you look at the second part, it said it creates four segments. 1, 2, 3, 4. And we can develop some type of a relationship or form a conjecture based upon this. Again, I'm not going to hold you responsible for the Explorer part. We're going to focus on these types of problems, okay? So the first thing we'll look at is in the Explain 1. If we have two chords that intersect inside a circle, we can derive a formula that says the products of the lengths of the segments of the chords are equal. So in other words, this is our first thing we're going to talk about. It's the chord-chord product theorem. Again, we have a chord and another chord, and the product part involves this. We know from here, since these two chords intersect each other, we can see that the line segment AE times the line segment EB will equal the line segment C times E, or the line segment CE times the line segment ED. So again, that's our first rule we're going to run across. Again, we can use this and a little bit of algebra, and we can find these lengths. So we can find length AE, we can find the length BE, blah, blah, blah. You'll see when we get to it, okay? All right, the next part is examples. Again, example 1A, they did the work for you. Example 1B, again, going back to that previous rule, the chord-chord product theorem. Again, we know that HG, the segment HG, times the segment GJ will have to equal KG times GI. So again, if we want to find out what X is, we have to go and apply the chord-chord product theorem. So we see the length of segment HG is 9. The length of segment GJ is 8. Multiply those guys, and then the length of KG times the length of GI is unknown. And from all this, we can figure out what x is. And from down below, we can now find what the length of each segments are. So we can figure out that what the length of HG is. It's going to be, well, we know it's going to be 9 plus 8 is 17. And we can find the length of KG and KI. Well, we already know that, GI. We already know that GI is bounded up here as 12. So again, we can see just from using the chord product theorem, we can figure out the lengths of these two chords. All right, so the your turn part, here's our picture. We already been given that the length of the chord AD is 12, and we want to find the value of x, okay, which is in this case CE, and the length of each chord. So we already know that this chord right here is 12, but we need to figure out what this chord is. All right, so setting it up using our chord product theorem, AE times ED has got to equal CE times BE. So using a little bit of common sense and a little bit of math, well, we know AE is 3, and we're going to know that ED is going to be 9 because we already know that AD is 12. So if I take 12, subtract 3 from it, I'll get ED. Then C times E is our unknown variable, and then E times B is 14. So from here, it's all algebra. So I know 12 minus 3 is 9, 9 times 3 is 27, x times 14 is 14x. Divide both sides by 14 and round it off to be 1.93. You're allowed to do that, or you can leave it as a fraction, doesn't bother me. And we can see now that the length of CB is going to be 1.93 plus 14, which gives us 15.93, and we already know the length of the chord AD is 12 because they gave it to us. So that is how we use the chord product theorem. All right, so let's go on to the next part. The next part is the secant product theorem. Now again, not to be confused with the trigonometry secant, not to be the same. So at the top I've highlighted, a secant is any line that intersects a circle at exactly 2 points. So again, basically what they're saying is if I look at AE, this is a secant, and it has intersects a circle at exactly 2 points, 1 point, 2 points. So this is a secant. Okay. Then a secant segment is a part of a secant line with at least 1 point on the circle. So again, this is going to be a secant. Okay, at least 1 point is on the circle, and a secant that lies in the exterior of the circle, that's going to be called an external secant segment. So this right here, BE and DE, are examples of a external secant segment that's outside the circle. So the secant product theorem says this: if we have two secants intersect in the exterior of a circle, so we have this secant AE and this secant DE, they intersect at a point outside the circle, then the product of the lengths of one secant segment and its external secant segment equals the product of the lengths of the other secant segment and its external secant segment. Well, blah, 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 blah. Man, I say that 3,000 times. In other words, what it's saying here is if I take the secant of AE and I multiply it times the external secant of BE, it has got to equal CE times the external secant of DE. So that is the secant product theorem. Again, we don't need to know the proof of it. So here, application, letter, example 3A, they did one example for us. You're more than welcome to stop the video and do letter B. Again, I'm going to go and just show it to you. My little dog is over here touching me. She needs to go outside. I'm going to wait until I finish up this video. So again, letter B, you're more than welcome to stop the video and try it. I've set it up for you. All right? So stop the video and try it. See if you get the right answer. And at the same time, after you get done viewing letter B, I want you to stop the video and I want you to do the your turn. All right, you're back from stopping the video. And I, on purpose, only did number 6 because I want you to do number 7 and go to the solutions manual, and they give you the answer to the your turn number 7. Okay, so number 6, find the value of x. All right, well, setting it up, we have PT, that's your line segment, and PR, another secant segment. Then we have our external secant segments. So we know that PT times PS has got to equal PR times PQ. So there's the setup using the secant product theorem. All right, so go here. So PT is going to be 4 plus X, and then PS we know is going to be 4. PR, if you look at it, is going to be 5 plus 5.4. That's where I get the 10.4. And then the PQ is 5. So from here, it's all algebra. So again, distributivity, multiplication, we get 16 plus 14x equals 52. Solve for x. We know x is going to be 9. As we divide both, subtract both sides by 16 and then divide both sides by 16. Did I say, okay, no. Subtract 16 from both sides and then divide both sides by 4. Pay attention. So we have found that PT will be 13 and PR will be 10.4. So that is the secant product theorem. And we have one more. Like I said, these are relatively easy. The next one deals with the secant tangent product theorem. So we did 3 of these. So the first one we dealt with was the chord product theorem. The next one we did is the secant product theorem. And now we're going to do the secant tangent product theorem. So again, you got to be able to distinguish the difference between these two. So very simple. Here we have a secant of AC, and we have an external secant segment of BC. But if you look here, this CD, that's a tangent. All right? It's not a chord, it's just a tangent. And we're going to find that the secant tangent product theorem says this. If I take the secant, AC, and multiply it by its secant segment, BC, it's got to equal DC squared. Again, be very careful in this part. It's not D times C squared, it's DC squared. All right, so that is the secant product theorem. Now again, this one, I think I got to do a couple of these. I'm going to do 3 more of these. Example 4A is a good real life problem. I'll let you guys study that. But let's look at the second one, okay? Let's see. Here's our example. We want to set up an equation according to secant tangent product theorem, and here's our problem we want to solve for x. So here again, here is our secant, which is 2 plus x. Here is our secant segment, which is 2. And then here is our tangent, which is BA, which is 5. And we have to square it. So all we got to do in this case, this is all simple algebra. All right. Now what I want you to do now is I want you to stop the video and I want you to go to the your turn. And I'm going to do number 10, and I want you to try on your own number 9, and then go to your solutions manual. I'm not going to focus on that one. That one's a little more applicable. You guys can do that. So look at number 10. Here we go. Here we want to find out what the value of x is. So we're going to use the secant tangent product theorem. Here's our secant of AC, which is 10. The secant external segment is BC is 4, and the tangent is x. Setting it up, You got AC times BC has got to equal CD squared. So we have 10 times 4 equals x squared. And we have 40 equals x squared. Now this one's a little bit different than the one that we did in part B of example 4, because now we have a quadratic. So this is going to give us two answers, but we're going to only focus on one of them. You're going to say, why only one of them? Well, you'll see in a second. So the next thing I did is I extracted the root, so that means plus or minus the square root of 40. Now again, since we already have our calculator, all we got to do is use our calculator. And that gives us 6.324. I don't know how far I went up. So again, if you take this whole problem, if I round it up to the nearest whole number, or in this case I went to the nearest hundredth, again, I don't have this here, but it's really x equals plus or minus 6.32. Now we have two answers here. One's plus or one's minus, but again, if you go back to this direction, back to this problem here, we're trying to find this length. And this length can never be a negative value, so your answer has got to be plus 6.32. So that is chapter 15, section 4, secant relationships in circles. All right, go on back. You may have to watch this video again. It's a relatively easy section. Thanks, guys. Catch you later.